One of the questions that we want to answer in this section is how do we transfer control from application programs to the operating system and back? So we call this protected control transfer or just control transfer. And there are actually two decisions that we're going to have to make. One is when should we transfer control? And the other is how do we transfer control? This video is mostly about how we transfer control, and we're going to do a pretty high-level explanation. We'll talk about the details of how the x86 does this, and then in later material, we'll step through this in excruciating detail to follow things like a page fault and how that transfer of control happens. But for now, let's figure out how do we transfer control from an application to the operating system. Now, there are three different kinds of control transfers we do, and we give them different names. So for example, we've talked about one all semester, which are system calls. So system calls are when an application explicitly asks the operating system to do something. So there's no mystery here. The application is saying, I can't do something, I need you to do it for me. And so this is an explicit request to transfer control to the operating system. And so because it's an explicit request from the process, we say that it happens synchronously with respect to the process. That is, the process knows exactly when this control transfer is going to happen. Another way that we can transfer control to the operating system is implicitly with something called an exception. So what's an exception? Well, one example is, have you ever written a program that inadvertently divided by 0? You might find that if you do that, your process crashes and it exits. So an exception is something that happens because the program did something, so it is still synchronous with respect to the program, right? The program did the divide and now you got the exception. However, you weren't intending for the operating system to take over, because it is very rare that what the process really wants is, hello, operating system, could you kill me because I'm about to do something stupid, right? That's not really what happened. What happened was the program did something, the hardware said, you're not allowed to do that. That invokes a control transfer to the operating system, and then the operating system takes some action. In many cases, the operating system will kill the process. In others, the operating system is going to do something to allow the process to continue execution. So these are both synchronous with respect to the program, or they happen because the program did something. But in one case, the system call, it was an explicit request for a control transfer. And in the other, it was an implicit request. It was like, I did something wrong, please fix this. There's a third category, which are interrupts. And these can happen at any time. So they are asynchronous with respect to the program. And the most common ones we usually think about are things like, I asked for the disk to go do something, the disk went off and took forever because we know that disks are slow, and eventually the disk is going to respond, and it is going to respond by generating an interrupt. So, excuse me, I'm done now. Please pay attention to me. So an interrupt is something that is usually triggered by an external event, although we'll see cases where it's an intentional internal event from the operating system. So some event happens, and because that event happened, we transfer control to the operating system because the operating system is the only one capable of responding to that event. Let's begin by looking at trap handling in the abstract. So in a general way, how it happens on all processors, and then we'll look at specifically how we do control transfer on the x86 processor. So the first thing we're going to do, so the mechanism that we use to transfer control is called a trap. So we have different kinds of traps, right? System calls, exceptions, interrupts, but the mechanism that transfers control is called a trap. So the first thing we're going to do is we're going to assign each trap a different number. So for example, and these aren't any particular processor, we might say, okay, all system calls, we're going to give the number 1. If the timer generates an interrupt, we'll call that 2. If the disk does an interrupt, we'll call that 3. And if another processor tries to interrupt me, which can also happen, we'll give that a 4. And so we'll give these traps different names, different numbers. And so when the operating system starts up, part of that process, which we call booting, right? So when the operating system boots up, what it does is it has a table. It says, here are all the things I need. Here are all the functions that I'm going to use to respond to traps. And so for each trap number, I am going to put a pointer in this table to a function that will get invoked on that trap. So in this first entry, I would put something that handles the trap for 0. In this one, as you can see, here is the trap handler, the code that should execute when my processor gets a trap with a value of 1. So if a process makes a system call, what the library code is going to do is cause a trap to happen. It will cause a trap with a type of 1. The operating system takes over and says, aha, I have a trap of 1. I am going to dispatch from this location to my trap handler, and I'm going to go respond to it. Okay, so for example, let's say that the operating system asks the disk to do something. So it sent a request off to the disk. Disks take forever, and eventually the disk says, I'm done, I'm done. And so what it does is it sends a message to the processor, and this message is basically an interrupt saying, excuse me, I'm done. The processor says, ooh, I got a trap of type, let's see, disk interrupt 3. So it goes to this table and it says, execute the code that this table entry is pointing to. And the next thing we know, our processor is executing inside the trap handler for that IO. So at a high level, at startup time, we initialize a jump table with pointers to a bunch of functions that are going to get executed when traps happen. And then when the trap happens, the processor turns control over to the operating system and says, deal with this. Okay, now let's look at the x86 in a little bit of detail. So I said that there's this thing called the trap table. In the x86, we have this thing called the interrupt descriptor registers. So these are hardware locations that contain special objects called gates. And in particular, what a gate is going to do is let us change privilege levels in the processor. And in particular, we're going to allow going through a gate to let us go from a lower privilege segment, i.e. your application which runs unprivileged was running, and we're going to use the gate to let you suddenly be executing in a higher privileged process, segments which we hopefully have talked about already in class. And so what happens is we initialize at boot up time, we initialize these gates to allow a trap at any time to transfer us into the operating system with the right privilege level. When we return through a gate, then we return the privilege level to whatever it was before. So you can think of this as like a physical gate where you have a security guard that says, ooh, you were running at unprivileged level. I'm going to open the gate, let you run at privileged level. But if you ever go back out through the gate, i.e. you stop executing in the operating system, then I'm going to restore your original level. So I said these are hardware registers in the processor. They have evolved over time. So initially they were called programmable interrupt controllers, or PICs. Then we got advanced PICs, APICs. And the most recent ones are called local advanced PICs because we have multiple of them because we need one for each CPU in the system. Okay, and so each one of these sets of gates has wires that you can hook up to 16 different devices. Okay, and so each one of those devices gives you a particular entry in this dispatch table, essentially. So you can think of these gates as really fancy dispatch tables. And so what I do as the processor is when one of these signals goes up, I can change the privilege level in the processor and then direct control to the right trap handler. And like I said, when we get to handling things like page faults, we're going to go through this in a lot of detail. But let's right now just talk about system calls in particular. So it turns out that, again, the x86 is the result of a long evolution in its processor history. And so it has gone through many different ways that we make system calls. And so if you look at older operating systems compared to newer operating systems, you will see that they make these calls in different ways. So originally, so old Linux systems used a single designated int instruction, which triggered what we call a software interrupt, which is a trap, but it was synchronous with respect to the processor. You're like, oh my God, you're throwing all these words and now using them differently. Okay, so what happens is that this int instruction makes the processor behave as if there were a trap, And then the operating system was only allowed to have one handler to handle this int instruction. So what the system had to do is it would take the int instruction. You're allowed to indicate some other information like, oh, a system call number, and it would say, oh, okay. So I just got this int thing. This must be a system call. The value associated with it is 57. I will go execute the system call that corresponds to the value 57. So the way system calls were implemented was that you did an int, operating system went off and implemented the system call or executed the system call, and then did an IRET for interrupt return and transferred control back to the process. Modern Linux systems tend to use a pair of instructions called sysenter, sysexit. They basically do the same thing. They allow you to transfer into kernel mode and return from kernel mode. But depending on which processor you're using, there are another pair of calls called syscall and sysret. And so in that case, and usually this is depending on whether you're on Intel or AMD, you don't need to actually know the details of which instruction is being used. I introduce it so that when someone uses these terms or talks to you or says these things or even asks you about them in an interview, you go, oh, this is basically how the x86 does trap handling. Right? That's what you really need to understand. And in particular, this is how it implements system calls. So we're going to wrap up here and remind you that the operating system is really just another program, right? It's written by programmers. The thing that makes it different is that the operating system is the code that we allow to run in privileged or supervisor mode. And this is a special mode in the processor that lets it do things that we don't let regular processes do. The way we transfer control is dependent on exactly the mechanism that the processor provides, and different processors provide different mechanisms. But they all do essentially the same thing, right? We're going to have a trap. It might be a system call, it might be an exception, it might be an interrupt. At some point, the processor gets a notification that we need to switch modes into the operating system. And at that point, it looks at the information that came along with that trap and decides what code to execute based on that. And that decision is based on information that got set up when the operating system booted. And you should definitely make sure that you understand the difference between a system call, an exception, and an interrupt. And there's sort of two dimensions to think about it. One is, did the program explicitly request something to happen? And two, do we know sort of when the event is happening, or could the event happen at any point independent of where we are in the program? So those are the things to take away. We'll spend lots more time in class talking about this.